All right, everybody, welcome back. And today's final lecture will be given by Professor Ben Feldman from Stanford. And Professor Feldman is interested in exploring the correlated electronic states and topological phenomena in nanoscale quantum matters and devices. And his topic today is going to be exploring the magic of twisted trilayer graphene. Welcome.
All right, so thank you guys. Thanks for the introduction, and thanks for sticking around till the end of the day. So today I'd like to tell you about some work that we have done in the last couple of years or so, looking at twisted multi-layer graphene systems. So these pictures give a little bit of a flavor, but I haven't put any axes or scale bars on them. And I guess I want to draw your attention, and knowing that I do scanning probe microscopy, think to yourself, what is the length scale of this image here that I'm showing? You'll see later on in the talk whether you're correct or not. So before getting into the details, into the nitty-gritty of the experiment, I want to kind of put this in a broader context that, generally speaking, as condensed matter physicists, some of the most interesting phases of matter can be tied back to a couple of key ideas. And really, these ideas have been decades in the making. They're very challenging experimental systems to study very challenging theoretical problems. And so although we've made quite a bit of progress, there's still a lot to be done. These two ideas are electronic interactions, which can give rise to a whole host of different phases. So here I've just shown an example phase diagram of high temperature superconductivity taken from a review article. And you can see there's everything from magnetic phases to superconductivity to things that we still to this day don't have a full understanding of exactly how to treat them theoretically. And likewise, topological phases of matter, although they came back to the fore relatively recently, actually date back also quite a long time. These are situations, one of the kind of best known examples and most studied examples are when you have a two-dimensional electron gas and you apply a magnetic field to get to a quantum Hall regime. These things can exist in those sorts of systems, but also there have been material progress that have been made to identify materials that intrinsically have some sort of topological invariant in them. And of course, we've heard several examples throughout the course of this conference that where people have been even up to very recently observing new phases of matter. And so I think a big goal, again, overarching goal of the community is to better understand and characterize these two threads and see whether any of the interesting physics that comes out of them possibly even could be technologically useful. So the unfortunate fact of the matter is we, for many of these systems, we're really under the tyranny of chemistry. So you need to find the right material system. There is some level of chemical bonding, et cetera, that dictates the properties of materials. And in many cases, these are very complicated materials with many different kinds of atoms. And that makes it hard to grow pure materials. And what I'd like to kind of talk about is a new platform where you make use of simpler starting blocks, van der Waals materials. These are two-dimensional layers that you can stack on top of one another in really very arbitrary ways. And in doing so, you can control all sorts of properties of the material. In particular, I'll talk about band structure engineering and how this can give rise to new properties. And of course, you've seen this already, that if you stack these materials and twist them relative to one another, there's a new periodicity that can develop, the Moiré superlattice periodicity. And by controlling various tuning knobs, could be twist angle, but also could be electromagnetic fields or strain applied to the system, this now gives a new playground that's highly tunable to get back at some of these long-standing questions. What happens when electrons interact with one another? How do you treat this theoretically, and what sorts of cool phases can come out from them? So this is kind of a series all focused on Moiré systems, but broken down by different class of materials. So today I'll tell you about twisted trilayer graphene, where you have 3 graphene layers that you stack with various different angles. And I'll show you a few different examples of the sorts of physics that we get out. And then tomorrow I'll go back to transition metal dichalcogenides, which we heard about yesterday in these twisted systems. Also, actually in both of these examples, there are aspects of strong electronic interactions married with topological phases and edge modes that come out in these systems. All right, so today's about graphene. I'll start at the very basics, build up one layer at a time. So here's graphene. It's a honeycomb lattice of carbon atoms, as you are probably all aware. Okay, so this is the real space picture. In momentum space, the low energy electronic states sit at these corners of the Brillouin zone at what are known as the K and K prime valleys. And in graphene, you have this linear dispersion. So you have a Dirac cone, and the Fermi level, the charge neutrality point, is right where these cones meet. So graphene on its own is a semi-metal. And to start building upon this, I want to think about 2 limiting cases when you have 2 different layers. And in particular, 2 different layers twisted relative to one another. So first of all, you can imagine adding a second layer that has a large twist angle relative to the first. The real space picture looks like this. In momentum space, also, the Brillouin zones are twisted relative to one another. And if this twist angle is very, very large, then what ends up happening is the low energy electronic states, which sit at these K and K prime points in each layer, are actually very far separated in momentum, and therefore up to some fairly large energy beyond what we typically care about in the low energy or for low energy states. These 2 layers, these 2 Dirac cones coming from each layer, don't talk to one another. They don't hybridize. And so what you get are 2 electrically decoupled systems that you can actually independently tune the carrier density in each with an applied electric field. So I'll come back to that. The other limit is maybe more familiar and maybe has drawn a lot more excitement. That's if you have a small twist angle between the 2 layers. In that case, still, you have some small separation between the low energy states at the corners of the Brillouin zone. But as long as your angle is small enough, at some energy scale, these 2 Dirac cones will cross one another. And because of the interlayer coupling between, or the tunneling of electrons from one layer to the other, this will open up some sort of hybridization gap. And so the idea is this hybridization gap opens up, and if you perfectly match this momentum offset between Dirac cones originating in the 2 layers with the magnitude of this hybridization gap, then what you get out are flat electronic bands that are really flat almost throughout this mini Brillouin zone here that's made up when you fold in due to the long wavelength Moiré pattern. And so this is just a picture here. You get actually 8 flat electronic bands that are separated by energy gaps to more dispersive bands. This factor of 8 comes from, you can think of these 2 Dirac cones, the spin and the valley degrees of freedom in graphene. OK, so as you know, when you have flat bands, correlation effects often dominate over the kinetic energy. And indeed, from the very first observation of this magic angle graphene, where the magic angle is set by, again, this competition between hybridization and momentum separation, the Dirac cones is about 1.1 degrees. The very first observation was that you get superconductivity and correlated insulating behaviors when you partially fill these flat bands. So this corresponds to half filling one of the flat bands. And at face value, it looks very similar to the high temperature cuprate phase diagram that I showed earlier. I think this may be a red herring, the similarity, except to say that in both cases, electronic interactions are very, very strong. And so when that happens, you get funny physics coming out. In other samples, so it's not just insulators, it's not just superconductivity. There are reports of, or a report of the quantum anomalous Hall effect in a particular device. And details will vary from sample to sample in terms of which correlated insulating states appear, exactly where does the superconductivity appear, and all of this can depend on details of sample fabrication, which is not super well controlled, such as what is the strain that's built in after you make these devices, what is the specific twist angle, and even to this day, I would say it's not fully resolved. What is the quote-unquote intrinsic behavior, and even though there are certain features which come back again and again. Now, I'm going to put a little asterisk here for correlated insulators, because when you do a transport measurement, you see a resistance peak. And indeed, it shows insulating temperature dependence. But actually, if you measure electronic compressibility, so this is a measurement from Shahalilani's group using a scanning single electron transistor, what you find is that actually at half filling, say at 2 carriers per Mori unit cell, there's no peak in inverse compressibility, which is what you would expect for a gapped phase. And instead, you get this kind of funny sawtooth pattern in electronic compressibility. So even though you have some sort of very resistive feature, generically speaking, that does not guarantee that you have a truly gapped electronic system. So there are some cases, and I'll show you some examples, where gaps do really emerge, and then you expect a peak right at some integer filling of number of electrons or holes per Mori unit cell. So that's just a comment to keep in mind, and this sawtooth pattern will come back again later on in the talk. That's the zero field phenomenology. At high magnetic field, also interesting things develop. So twisted bilayer graphene is a two-dimensional electron system. Again, you apply a large electric field to that, and you reach the quantum Hall regime. You have Landau levels separated by some cyclotron frequency. I guess I haven't shown it for graphene because these are evenly spaced. Sorry about that. And in general, what that means is that when you put your Fermi level between 2 Landau levels, then the bulk of the sample is insulating, and the conduction happens through these chiral edge modes, and so you get these dramatic signatures. There are plateaus in the Hall conductivity and zeros in the longitudinal conductivity. The details of this, how these states evolve in a magnetic field, are dictated by the Strata formula. So even if you didn't have information about electronic transport, actually you can still figure out what's going on just by looking at the slopes of a given state as you tune the magnetic field, how they change in density. Now, the situation in Mori systems is a little bit more complicated than that uniform two-dimensional electron gas, because in Mori systems now you have some electronic supermodulation. And so you effectively get interference between the magnetic length scale and the length scale of this electronic modulation. In the low magnetic field limit, so the spectrum looks like this. What this gives rise to is what's known as the Hofstadter's butterfly spectrum, or a fractal energy spectrum. In the low field limit that's down here, these things look very much like Landau levels. But as you approach something close to 1 flux quantum per electronic unit cell, then these things break up, and you see these sort of self-similar mini gaps appearing in the spectrum. And in general, again, these Hofstadter states have some non-zero Chern numbers, and that means that when you park yourself within one of these gaps between these Hofstadter subbands, you get a sloped feature as a function of magnetic field, and when plotted as a function of carrier density. Now, in twisted bilayer graphene and magic angle twisted bilayer graphene, still the starting point is flat electronic bands. So still, all of this entire Hofstadter spectrum that you see actually has a very small window in energy, and again, correlation effects dominate. And what has been observed in many, many samples is that there are Chern insulators that appear at some finite magnetic field. These, again, they're sloped, so these are zeros in RXX that I'm just taking from, this is data from Dmitry Avitov, but there are many, many groups who have seen this. And oftentimes, the strongest states are these particular states that have a Chern number 1 that comes back to filling of 3 electrons per Mori unit cell, Chern number 2 coming back to 2 electrons per Mori unit cell, and Chern 3 state that goes back to 1 electron per unit cell. These you can understand in a picture, again, it's a high field situation here, and so you can think about these in terms of the Chern numbers associated with the gaps in the Hofstadter spectrum of magic angle graphene. Again, there are 4 spin and valley flavors. So you have 4 copies of a Hofstadter spectrum like this, and if you just fill up, say, to this gap right here, which has a total Chern number of 1, and you fill it with 1 flavor, then you get a Chern 1 state. So full filling is 4 electrons per more unit cell. So at 3, you basically there's one, you haven't filled this upper band for one of the layers, so you get a Chern 1. Here, you fill 2 of the flavors up to this point. You get a Chern number of 2. They just add that way, and similarly for Chern number 3. And so you can understand these Chern insulators that way. Just in terms of some sort of symmetry breaking, you're picking a particular set of spin and valley flavors to populate preferentially in a magnetic field. So that was meant to be kind of an introduction to magic angle graphene. If you didn't follow all of the details, that's OK. All you really need to know is this schematic phase diagram. So once again, Ali Yazdani to the rescue. This is from one of his papers and really shows all the features that I want to highlight here. So one is that, well, OK, so there is some superlattice gap between the flat bands as you fill from the charge neutrality point to 4 holes per more unit cell. At half filling and even sometimes other integer fillings, you get some sort of correlated insulating behavior. And as you apply a magnetic field, you get these Chern insulator states and general broken symmetry quantum hole states that come out from the charge neutrality point as well. And I would say, kind of as a starting point of our understanding, there's still big questions. Even though we know that these Chern insulators, for example, are associated with picking particular subset of spin and valley flavors, we don't know what those flavors are. There are big questions about generic behavior. So when is this truly thermodynamically gapped? When is it just a resistance peak, and what's the understanding of that? And of course, all of this is motivated because as you dope away from this correlated insulator, you get some sort of possibly unconventional superconductor appearing. All right, good. So there are some open questions in magic angle bilayer graphene, but I started off telling you this is not a talk about magic angle bilayer graphene. It's a talk about twisted trilayer graphene. So in this talk, actually, I'm going to consider a situation where you have 3 layers and 2 different twist angles between those 3 layers. So here is what we've been discussing already. There's some twist angle between layers 1 and 2, and then you can add on top of that a 3rd layer, and it also has some relative twist angle between the 2nd and 3rd layer. And so not only do you get a moire pattern, but actually you can get moire of moire physics associated with both of those combined twist angles in the system. And for the experimentalists in the audience, you might be wondering, why on earth would you want to do that? You just told me magic angle bilayer graphene is so sample dependent and so hard to make. God help you if you want to do something systematic with trilayer graphene now. And similarly, for the theorists in the audience, you're wondering, hey, it's already so hard to understand bilayer graphene. Why do we want to complicate this with the 3rd layer? But actually, I hope to convince you that by adding a 3rd layer, we can learn something about the physics of magic angle bilayer graphene. And not only that, we can also engineer new types of behaviors by adding that 3rd layer, which wouldn't be possible just with 2. So in this talk, I want you to think about or the goal that I'll be trying to explain is kind of addressing the question of how does this additional twist angle, how does the coupling to this extra graphene layer and the relative twist angles, how do those affect the electronic properties and the correlated states that develop in the system? And similarly, now you have 3 sheets of graphene. These are super thin, super stretchy, very prone to strain and lattice relaxation. And a big question, and you'll see it has a big effect, is how does this relaxation itself lead to different electronic behaviors? So just to point out that this is not all hopeless, and trilayer graphene also is interesting on its own right, Most of the studies so far on twisted trilayer graphene have been looking at this so-called mirror symmetric magic angle twisted trilayer graphene. So that corresponds to having two equal but opposite twist angles. You start with a layer, you twist in one direction, the third layer you twist back. So this has some connection to magic angle bilayer graphene and indeed has very, very similar phenomenology. So again, as you fill a certain number of electrons or holes per more unit cell, you can see that there are correlated insulators which are appearing at integer filling. These giant blue swaths here are superconductivity that appear. Now, an electric displacement field actually has some effect on the physics. Again, you see if you measure electronic compressibility, not truly gapped thermodynamic phases, but rather this characteristic sawtooth and inverse compressibility. And if you apply a large magnetic field, again, you see that there are these diagonal features that come out in a magnetic field. These are Chern insulators, just like was seen in magic angle bilayer graphene. So in some sense, one expects that twisted trilayer graphene also is a really maybe a helpful platform to try and disentangle what is intrinsic, what's really needed to give rise to these characteristic behaviors of correlations in the system. So that'll be the goal of this talk. So really this talk is a three-part talk, I'll be talking about three different samples, but really two different ideas, two different limits of twist angle. So I'll tell you about first a case where the two twist angles are very different from one another. One's relatively small twist angle and one relatively large twist angle. And I'll show you that that actually gives rise to decoupled electronic subsystems where one of them behaves like magic angle graphene and one of them behaves like monolayer graphene. Along that same theme, we have another device that also has a mismatch in twist angles, one small, one large, and we can use our scanning probe microscope to explore as a function of spatial position when do you see the characteristic strong correlations, and how does that compare to what's observed in just bare magic angle bilayer graphene. And finally, with whatever time is remaining in this talk, I'll tell you about a completely different system where both twist angles actually are small, helical trilayer graphene, where you get large effects of strain and atomic reconstruction, and you get large domains with conducting boundary modes between them. All right, so let me go ahead and introduce the first sample. It consists of 3 graphene layers. And the twist angle, I'll show you how we know this in a second, between, say, the bottom 2 layers is about 1.1 degrees. But the twist angle to the third layer is large, greater than 5 degrees. Just looking at the optical slide, as we were picking up layer by layer by layer and stacking the materials, it looks like one of them, we didn't aim for this, but one of these layers rotated a lot during fabrication and nonetheless turned into something interesting. This is a dual-gated sample, so we have a bottom gate and a top gate. That means we can tune the carrier density in this trilayer graphene and also the electric displacement field that's applied to it. And this entire sample is etched into a Hall bar. So we make edge contacts in this Hall bar geometry to all 3 layers simultaneously. So you should think of the transport measurements that I'll be showing you as kind of parallel transport through all 3 of these layers at once. So I've already told you that if you have a large twist angle between 2 graphene layers, it effectively acts as 2 electrically decoupled systems. And so you might expect, and indeed this is what we observe, that really these 3 graphene layers turn into 2 electronic subsystems, one of them which is monolayer graphene and one of them which is magic angle graphene. And by applying an electric field perpendicular to the sample, we can tune the relative energies of electrons living in these layers and therefore control their relative chemical potentials. So what does this look like? If we just do a transport measurement, this is a measurement of Rxx across these contacts here, as a function of carrier density, the total carrier density in all 3 layers, and the displacement field applied between the layers. And this is somewhat funny looking. It puzzled us when we first saw it. You'll notice there are a lot of bright features here that corresponds to resistive states. And then there are some weaker features that I'll come back to that sort of go kind of more vertically in an S-shaped curve. Now, because we're starting from this description of monolayer graphene and magic angle graphene. Monolayer graphene, we know the highest resistance states should occur when it's at its charge neutrality point. So the highest resistive features here, we're going to associate with a situation where the monolayer graphene, the chemical potential is right here at its Dirac point. And if we just take a cut along this line here of resistive features and plot it as a function of number of electrons or holes per more unit cell, again, you can see these sort of characteristic peaks at integer fillings. These are the correlated insulators that I was telling you about before. And so we can associate kind of this black line here with a situation where the monolayer graphene is at its charge neutrality point, its chemical potential is equal to 0. So what about so this corresponds to the superlattice gap out here, the superlattice gap on the other side. This is charge neutrality in the magic angle graphene. And as we're moving along this line, we're changing the doping in this magic angle graphene subsystem. But let's say we pick one of these states, say nu equals 2 electrons per more unit cell in the magic angle graphene subsystem. You can see that this resistance peak persists in this sort of S-shaped curve as you go, or you could look at the charge neutrality point here. And that corresponds to a situation where you're tuning the monolayer graphene chemical potential, you're filling or depleting electronic states there while maintaining a fixed filling in the magic angle graphene. And this shape here corresponds actually to what you would expect for a change in chemical potential as a function of energy for a Dirac cone. So it has a characteristic square root of density shape. And so this resistive, this plot of resistance that you're seeing here that has this sort of antisymmetric behavior as a function of density and displacement field is nothing more than a confirmation that we have electrically decoupled monolayer and magic angle graphene systems. So that's the case. Oh, yeah, question.
Between the HBN layers and the outer graphene layers?
Good question. Yeah, thanks for that, and please interrupt as I go. So relative stacking is about 1.1 degrees. So if you say this is 0 carrier density in monolayer graphene and ask what does this density correspond to in terms of twist angle, you get 1.11 degrees. So the low twist angle, what I'm calling magic angle graphene, subsystem has about 1.1 degrees between it. We don't have an experimental way to know exactly what this twist angle is between, say, the middle and top layer here. But from an optical image, just looking at the flakes as we were doing the stacking process, it looked like it was greater than 5 degrees. And again, electrically, they at least appear decoupled from one another such that you can maintain carrier density in one and tune carrier density in the other. So it should be a large angle. And then you asked about the HBN. We don't see any sign of HBN alignment. So for example, when you have HBN alignment to magic angle graphene, you expect to get quantum anomalous Hall physics, say at filling of 3 carriers per more unit cell, and we don't see anything like that. We don't see a large gap at charge neutrality that also should appear. So as far as we can tell, there is no alignment to the HBN. All right, good. So that was the case at 0 magnetic field. And it's also sort of interesting if you think about what happens now as you apply a perpendicular magnetic field to this sample. Still, the layers remain electrically decoupled. So this is, again, a map of longitudinal resistance, Rxx as a function of total carrier density. And sorry, I lopped off the axis here, but this is as a function of electric field or displacement field, same scale as this image was. And so here you can see there's a lot more structure. But again, we can understand it in exactly the same way. When monolayer graphene is in a magnetic field, you get Landau levels. So everything within this little box that I'm outlining here with my pointer corresponds to filling factor 2 in monolayer graphene. So this is now quantum Hall filling factor. This little box below the black line corresponds to filling factor -2. And you can sort of follow individual states, and they have this sort of staircase-like pattern that corresponds to, again, maintaining a particular carrier density in the magic angle graphene and filling 1 by 1 by 1 Landau levels in the monolayer graphene. And likewise, and I'll come back to this more later, in magic angle graphene, when you apply a magnetic field, you should get a Hofstadter spectrum developing. And so there should be quantum Hall states and Hofstadter states that develop in the magic angle graphene subsystem as well. And still, these are electrically decoupled. And I want to point out something interesting about this system. So depending on what your carrier density is and displacement field is, you can tune to different regimes where the monolayer graphene and magic angle graphene subsystems have the same carrier density, or to situations where they have opposite signs of the carriers. One is in the electron regime, or one is electron doped, and one is hole doped. And if you think about what this means for quantum Hall states in that situation, if you have electrons in one layer and holes in the other layer, then that necessarily means that the edge modes, which are carrying your current in each layer, are propagating in opposite directions from one another. And there's an interesting question here, which is, how does the resistance that you measure depend on the details of the quantum degrees of freedom, the spin and Valley degrees of freedom in the monolayer graphene and magic angle graphene systems? These three layers are all etched into a Hall bar, so the edges are literally on top of one another. Because they're etched, we think that probably there's atomic scale disorder, so probably Valley is not a good quantum number. And I can't say anything particularly crisp about the Valley degree of freedom. But on the other hand, if we can say something about the spin degree of freedom. So if both of the edge modes have the same spin, then one can backscatter into the other, and you expect a large resistance to develop in that case. Whereas if they have opposite spins, at least in the absence of any sort of magnetic disorder, any sort of spin flips that are induced in the system, these two edge modes just flow right by one another and can't backscatter into one another. So this is sort of like an artificial quantum spin Hall insulator where one spin goes in one direction in one electronic subsystem and the other spin goes in another direction. So what that means is by looking at the details of the resistance that we measure now in this trilayer, we can learn something about the relative spin alignments of states in each individual layer. Yeah, question? Disorder in what sense? Sorry, disorder in... Oh, no, 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 I didn't say it's small. I expected there to be atomic scale disorder that not necessarily small. But I don't expect magnetic disorder. So there's nothing in this process that should introduce magnetic impurities. So spin should remain a relatively good quantum number. Does that answer your question? OK, perfect. OK, good. So that'll be basically the name of the game. The idea will be that we know what is the spin polarization from prior measurements of monolayer graphene. We know what each quantum Hall state, what its spin polarization is. And we can use that then as a probe for the magic angle graphene subsystem. So I'm going to start off looking just in the vicinity of the total charge neutrality point here. So this is right around total filling 0, where both monolayer graphene and the magic angle graphene have quantum Hall states that are emanating from their respective charge neutrality points. And so that'll allow us to address the symmetry breaking of these quantum Hall states that are circled here. So this is just blown up now at 8 Tesla, larger magnetic field. Plotted, again, RxX is a function of total filling factor in both layers and displacement field. And what we're going to do is we're going to focus on 0 total filling, that is, along this line here, along this vertical line here, you have equal and opposite carriers in each respective electronic subsystem. So if you just take a line cut across here, this is what the resistance looks like as a function of displacement field at a few different representative magnetic fields. So I'm just showing you the 8 Tesla data here. And we can think about what is the behavior in each respective regime. So right at 0 displacement field, 0 carrier density, this corresponds to charge neutrality for both the monolayer and the magic angle graphene. This is a broken symmetry state. The bulk is insulating, and there are no edge modes because it's nu equals 0. So you expect there to be resistive behavior. And indeed, there's a peak in resistance right there where right around d equals 0. You can see there's kind of yellow behavior and then some gap between that. That corresponds to situations where you have total quantum Hall filling 1 in each respective subsystem. So for example, the graphene may be in the nu equals 1 state and the magic angle graphene in the nu equals -1 state. And in that case, you expect 2 counterpropagating modes in each respective layer. And you'll notice that the resistance drops down and in fact is very close to this, the predicted quantized value for quantum spin Hall insulator of h/2e². And so what we surmise from that is that actually the spins in the monolayer and the magic angle graphene system, when you have just one pair of counterpropagating modes, these are opposite spin states. And we've realized the quantum spin Hall insulator, this matches what people have seen previously in large angle twisted bilayer graphene. It matches also what you expect just naively from the Zeeman effect. Yeah?
Why do your plateaus drift further away? Increased magnetic field?
That is a great question and not one I have a good answer to. So you can imagine, as was pointed out, these samples are not perfect. And it could be something related to bulk conduction. Actually, there are a number of experimental artifacts that I don't want to get into the details of here. We have a super long discussion of this in the supplement. Happy to chat with you later. But the real answer is we don't have a great idea as to why this is drifting downward. Yeah. OK. Yes.
The orientation of the spin current, or like of the turn current for the magic angle thing, if you exchange the layers, would it swap?
If you exchange
Like
layers.
the 2 layers of the magic angle twisted bilayer graphene subsystem.
Yes. OK, so remember, we're in a situation here where one carrier type is holes and one carrier type is electrons. And so if you just ask the question, Zeeman tells you want to fill a spin aligned state first, and you think through the order of filling different spins as dictated by Zeeman, then you will automatically expect opposite spins for one state that's an electron and one state that's a hole. Our presumption, although we don't have a parallel field to check this, is that it's really driven by Zeeman physics. OK. So then you can go to the more interesting case. So it kind of had to be this way. That is, you must have a spin polarized state. I guess it didn't have to be that they were oppositely aligned from one another, but that's at least what you would expect naively. But a more interesting question comes about when you have 2 electrons going in, 2 electron edges going in one direction, 2 hole edges going in the opposite direction. We know in graphene this is not a broken symmetry state. So this corresponds to a spin up and a spin down state in the monolayer graphene. But again, for the magic angle graphene, we don't know what is the order of filling. If you also have a spin unpolarized state in magic angle graphene, then you can get scattering between like spins, and you expect, again, this thing will have a very large resistance. And indeed, over here, this is what we observe. And so we take this as a sign that the magic angle graphene has a large, is spin unpolarized, and this gives rise to the large transport resistance that we observe. Here, it's less clear-cut relative to this h/2e², but again, the value of the resistance that we observe is larger than h/2e², and you can see there's this large jump up from the quantum spin Hall insulator situation where you have opposite spin types to this situation at up here where you have, again, a larger resistance, and we think this also is spin unpolarized. So we have other measurements of other contact pairs, non-local measurements, where in fact this resistance is even a larger fraction. And so we're pretty convinced that in both cases, when you fill 2 quantum Hall states, I guess I should just go to the next slide here, when you are looking at these nu equals 2 states coming from charge neutrality and magic angle graphene, these are spin unpolarized states. And so we can use this now to assign the order of filling different spin states in the system for these charge neutrality Landau levels. And I want to just quickly mention what happens now for what are the more exotic states, these Chern insulators, where you can play the same game. So a Chern insulator also has an insulating bulk and will have conducting boundary modes. And this is, so previously we were looking at kind of this zoom in here. This is the same 8 Tesla map of longitudinal resistance. And if you look in other regions, you can realize a situation where the monolayer graphene has filling 2 or filling -2, and the magic angle graphene is in a Chern insulating state, and you're in this counter-propagating regime of 2 electron-like states going in one direction and 2 hole-like states going in the other direction. And again, we can ask this question: what is the resistance that we observe in that case? Well, first of all, for this state where it's Chern number 1 coming from nu equals -3, and monolayer graphene is nu equals 1, so one pair of counterpropagating modes, actually the resistance blows up well above h/2e². So this is a sign that actually in this case the spins are aligned. Again, that's expected just if you consider Zeeman physics. So that's not surprising, but it's a nice confirmation that that this method works. If you look here on the whole side of magic angle graphene, that's this red line. Also, as you increase magnetic field, this guy is growing larger and larger as the Chern state gets stronger, and it's well above h/2e². So this is a sign that the Chern insulator itself, in magic angle graphene, is also spin unpolarized, just like what we had been talking about before. Curiously, actually, the resistance is lower for the electron side, and it matches very, very close to h/2e². So here, if anything, the data seem to be pointing to a spin polarized state where the two, so no matter what you have, you'll have at least one aligned spin. Those can backscatter. But if you have one remaining anti-aligned counterpropagating pair, then you expect just h/2e² resistance. And we see something close to that. And so tentatively, then, we assign this Chern insulator on the whole side to be spin unpolarized. And the evidence is pointing toward this Chern insulator on the electron side to be spin polarized. So there are some details there. Actually, the spin unpolarized case for the quantum Hall states is a little bit surprising. You would expect, again, from Zeeman physics, why not have both of the spins be aligned? It's a sign that there is some other symmetry breaking. Could be, for example, strain to the applied to the sample that is actually favoring this anti-ferromagnetic alignment. That's a little bit surprising, but as a broader picture, I want to just point out, I think this is kind of a neat way of looking at symmetry breaking in these twisted systems using some probe layer nearby to figure out symmetry of the broken symmetry of the system. OK. So where do we stand now? That was one example of a twisted trilayer graphene sample. But as I promised you, I'm going to talk about a few. And in fact, there's quite a large set of possibilities for the different twist angles that you can get. And everywhere along this kind of sloped line here corresponds to a situation where you expect a relatively large density of states, relatively flat electronic bands. So what have I shown you so far? Well, there was this point here where you have alternating sign between the two angles, but equal magnitude between signs. That's this magic angle twisted trilayer graphene that I flashed in the introduction. What we were just talking about was a case way out here where you have one angle very large and the other angle close to magic angle bilayer graphene. And so that we also spent some time on. There's one other experiment that I won't go into the detail, but I'll just point it out that in certain limits you expect quasi-crystalline behavior. And so there's a report there. All of these are on this alternating sign. So you twist one layer, and then you twist back by some amount with the third layer. But there's this entire window over here that has received relatively less attention. And it's there that I want to talk about for the remainder of this talk. And the measurements that I'll show you are with our scanning single electron transistor probe. And so I want to just quickly introduce that technique and what it actually measures. So a single electron transistor, you should think of just as some quantum dot or metallic island separated by tunnel junctions from source and drain electrodes. These tunnel junctions should have at least a quantum of conductance, and there may be some nearby gate that you can use to tune the energy levels in the island itself. And so if you think about the energetics of states within this quantum dot here, or metallic island, there are many, many states, but it's small. So there's a large Coulomb repulsion, a large charging energy, E squared over 2c, which is associated with adding one additional carrier onto this island. And so what that means is if this charging energy is large compared to the temperature of your system, then when you're in this scenario shown in panel A, where the leads, the Fermi level of the leads, lie within this charging energy gap, electrons can't hop onto the island, electrons can't hop off of the island, and so you get relatively low or no conductance in that scenario. But as you change the gate voltage, you can tune the energies of these states, and you can tune them to this sort of resonant condition where one of the energy levels in the island is aligned with that of the lead. So an electron can hop on, it can hop off again, and this can be repeated again and again and again. So this is one electron coming on and off at a time. That's why it's called a single electron transistor. And if you just look as a function of gate voltage, what you get are Coulomb diamonds. And so there's an oscillatory pattern of current through the single electron transistor from source to drain. And by monitoring this current, you can then figure out something about the electrostatic environment that it's in. So the SET, the single electron transistor, is very sensitive to the local electrostatic potential. And what we do is we fabricate one on the apex of the tip. So this is actually an SEM image of one of our tips. This is about 100 nanometers or so in size. There's a tiny island there. These are the source and drain electrodes. And what we do is we park it over some sample. Here I'm showing twisted trilayer graphene of interest, where now the sample that we'd like to study is the one which is providing whatever electrostatic gating to the tip. And the reason why this is powerful is what we can do is we can fix the electrochemical potential of the sample. So we hook it up to a battery. That's just the sum of the chemical potential and an electrostatic contribution. And if that is fixed for this sample, then as we're changing the carrier density, as we're applying a backgate voltage to the sample, that changes the carrier density, that changes the chemical potential. But because the electrochemical potential is fixed, any change in chemical potential mu has some corresponding opposite change in electrostatic potential. And that is what's sensed by the tip. And so through these measurements, we're effectively able to probe the chemical potential, or in fact, we do this AC, so we probe its derivative d mu dn. So just a little bit about the experimental setup. So the spatial resolution that we have is of order 100 nanometers or so. That's set by the height above the sample and the radius of the tip. I'll come back to that hopefully at the end of the talk. It's very, very sensitive in terms of how crisply you can measure mu or d mu dn. And the base temperature of this system is 330 millikelvin. So the measurements that I'll be showing you from here on out were taken generally around 330 millikelvin. So what do you expect to see? Well, let's say you have two flat bands. There are some peaks in the density of states, maybe some energy gap between them, or some low density of states between them. As you apply a larger and larger gate voltage, you fill up electronic states here. As you're filling this peak in the density of states, the chemical potential is relatively flat. It doesn't change very rapidly. But as soon as you go from, say, here up to here, for very few electronic states, now there's a jump in chemical potential before you get another plateau. And again, we measure typically the derivative of that signal so that any step in the chemical potential of your sample corresponds to a peak in d mu dn. And so anytime there's a low density of states, or an energy gap in the system, we have a very large experimental signal. So this is a great tool to look at gaps, whether they're single particle or many body gaps that develop in the system. OK, so what have we studied? There's a second sample, which morally seems very similar to the first. So again, we have one small twist angle, about 1 to 1.4 degrees. That we have a crisp handle on the exact angle. The other sample, twist angle is significantly larger. Again, we think it's about 3 to 4 degrees, but that one we have less precise knowledge about. And what we're going to do is we're going to park our tip above this twisted trilayer graphene and just measure what behavior do we get as a function of spatial position. So this white line here is this line cut. We're moving the tip along this white line over 4 microns, the color scale is inverse compressibility d mu dn. So yellow here is incompressible. That corresponds to an energy gap or a low density of states. And what you can see is as we modulate the density, there are several several yellow features which come about here. One of them is, well, there's a pair of them which you can sort of see dispersing outward like this. These correspond to the superlattice gaps in the twisted trilayer graphene. Everything in between is as you're filling the relatively flat bands. And these correspond, we can figure out what is the relative twist angle associated with those superlattice gaps. That corresponds to the small twist angle. The large one is kind of outside of our field of view. So again, we don't have a crisp knowledge of what that is. But you can see that it varies along this line cut from anywhere from about 1 to 1.4 degrees. And I'll point out that there are certain regions here where you see some extra features that are appearing in the middle. So as we're filling the flat bands, these you can just take line cuts and you can see they match very nicely to this sort of typical sawtooth and inverse compressibility that one observes. And in fact, these you can map out kind of what is the oscillation, how strong is this sawtooth, what's the amplitude of it as a function of this twist angle between those two layers. And what you find is that it peaks right around a very similar value for as you get from magic angle twisted bilayer graphene, even though this is now a trilayer with one relatively weakly coupled third layer. And so the physics is a little bit electron hole asymmetric. This is one of the questions that people have wondered in magic angle twisted bilayer graphene. When you only have one sample, oftentimes there's electron hole asymmetry, and it's not clear whether the differences from sample to sample and the electron hole asymmetry are what exactly the cause is. Here we're able to compare very crisply as a function of twist angle that there's magical behavior on both sides, but the quote-unquote most magic angle where these features are strongest is actually different for electrons and holes. So it's so there's a slight difference there, and we're able to look at this systematically. The other thing that maybe you can pick out by eye is that there, in addition to these features, there are some sharp lines over a small range. You can see them a little bit better in the line cuts. These are true thermodynamic gaps that happen right at filling factor 2, so 2 electrons or 2 holes per more unit cell. And again, we can map out what is the twist angle dependence for the electron side and for the hole side of these states. Again, there's a slight difference in terms of where is the strongest gap, and we can see that it's present in some places, but not in all. And so this, again, matches what people have observed for magic angle bilayer graphene. I think for interest of time, I'm going to skip through this just to say that one can look at the magnetic field dependence of these states also in a particular location, and it matches also very, very closely to the phenomenology that's observed in magic angle bilayer graphene. OK. So far I've shown you one limiting case. That is, you have a twisted trilayer graphene that has one small angle, one relatively large angle, and morally, it's very, very similar to magic angle bilayer graphene. So matches to maybe what you'd expect out in the tails of this wider field of view. What I want to switch to now is something that was recently theoretically proposed to be interesting, helical trilayer graphene. So what is helical trilayer graphene? Again, you have 3 layers. Again, you twist by the same amount for each layer, but now you twist in the same direction. And so when you do that, there is some moire pattern between, say, the bottom layer and the middle layer. There's some moire pattern between the middle layer and the top layer. These are nominally identical as long as the twist angles are identical. But when you have all 3 layers together, there's an additional extra length scale, a super moire wavelength that develops. The moire length scale is set, at least in the low twist angle limit, by the graphene lattice constant divided by the twist angle. But this super moire wavelength actually goes as the graphene lattice constant divided by the twist angle squared. And so it's much, much longer of a periodicity. And if you think carefully about what you expect for the Moray-Brillouin zone in this sort of system, actually, it's kind of interesting. So there are 3 layers. Each of them has, say, a particular valley, K1, K2, and K3 here. And the low energy states are sitting right around that valley. That is, each layer has some starting Dirac cone there. And they're almost aligned with one another. They almost line up, but not quite. But they're close enough that actually by slightly stretching locally one layer relative to the other, so if you make the middle layer corresponding to green here just ever so slightly larger, that moves its the corner of the Brillouin zone inward so that all 3 layers now line up in a line. And it turns out that this is energetically favorable, or at least is predicted to be energetically favorable in this helical trilayer graphene. And what it does is, locally, there is some uniform Moray periodicity with particular stacking arrangements of the sublattices on these 3 graphene layers. So orange and purple correspond to these kind of AAB and BAA stacking arrangements, and they themselves form a sort of honeycomb lattice. And the prediction is that this is the preferred stacking, and so you get large, it's favorable to slightly locally strain the graphene sample so that you get large regions of this uniform single Moray periodicity. There are actually 2 triangular domains that are different from one another that correspond to switching which sublattice is orange and which sublattice is purple. And then you get domain walls between those different stacking arrangements. Now, what does the band structure look like in this system? Well, just like all of these cases that I was telling you about, it's predicted to have flat bands right at the charge neutrality point that are separated by very large gaps to the more dispersive remote bands. And it's actually even more interesting than that, because individually, each of these triangles breaks C2Z symmetry. And so you expect that actually these flat bands here have non-zero Chern numbers that depend on the valley index and sublattice index. And not only do they have non-zero Chern numbers, so they're topological bands, but actually there are some bands that have Chern number 2 or -2. And furthermore, if you look carefully and sum up all of the Chern numbers corresponding to a particular valley, what you find is that when you're in this gap, for a given valley, you have a non-zero Chern number. Now, still, this is at least a zero magnetic field. There's nothing that breaks time reversal symmetry. The opposite valley has the opposite Chern number when you're in this gap. But nonetheless, you expect this to be sort of similar to the twisted TMD systems that were discussed earlier, where you have Chern bands that have some particular valley dependence, what the sign of the Chern number is. So this is all theory so far. But there was a recent experiment from Pablo Herrero's group where they made a helical trilayer graphene sample. It turns out that the magic angle for a helical trilayer graphene, where these bands are the flattest, is around 1.8 degrees. And indeed, when you tune the filling factor and displacement field and measure transport through the device, you can see that there are features at intermediate filling, so signs of strong electronic correlations. So you get the correlated insulators like I was describing before. If you park yourself at some of these states, some of which are integer, so for example, near nu equals 3, some of which are fractional, so near nu equals 2/3, there's an anomalous Hall effect in hysteresis. So it's not quantized, but at least it's suggestive that maybe there's something to this, that maybe there is some topology of the bands that is giving rise to an incipient Chern insulating state. This looks actually a lot like the very first measurements on HBN-aligned magic angle bilayer graphene, where, again, there was no quantized Hall resistance, but nonetheless, you could see these sorts of hysteresis loops. And I'll remind you that it's a little bit complicated in helical trilayer graphene, because if you're doing some global transport measurement, these domain walls will necessarily, or can very easily, affect what's the nature of the quantization. So it may even be that locally you have some quantized, some quantum anomalous Hall state, but the domain wall physics makes the transport difficult. So this is still an open question, but at least is very suggestive that this is an exciting system to pursue. Yeah, question.
Domain.
It is possible to cut a sample and take and measure across whatever you've cut. There's no guarantee whether you cut in the right spot, whether you have only one domain. For that, to know where to cut, you really have to have some microscopic tool. Okay, so we made also a helical trilayer graphene device. Looks like this, and we measure it. So this is a representative cut of d mu dn as a function of carrier density, and its integral, the chemical potential, as a function of carrier density. Indeed, if you look at this pink curve, the bands are very, very flat. The superlattice peaks that we observe here correspond to an angle of about, well, I guess I'll say it in a second. We don't see anything particularly intermediate filling. So this is not at the magic angle. And indeed, if you look along a spatial line cut along this black line, you can see that actually things are very uniform in terms of behavior along this line. We can extract the twist angle. It's about 1.45 degrees and only varies over micron length scales by a few hundredths of a degree. So this is a remarkably homogeneous sample. We can go one step further. So these, I guess I should say, these yellow features are the superlattice gaps that separate the flat bands from the remote bands. And we can go one step further. So we can measure as a function of spatial position in this white box here, looking at where this peak corresponding to full filling occurs, and extract the twist angle in this entire box, again, just a few hundredths of a degree over about a 2 by almost 5 micron area. So super, super homogeneous. And when we look at what is the corresponding electronic structure of this peak, now you start to see some supermodulation. So the length scale is quite large. This is a 500 nanometer length scale. This is the same size of the image that I've been showing you before. And you can pick out these sort of yellow honeycomb features. And what I'd like to compare them to is this schematic map of the different triangular H and H bar domains separated by these black domain walls and these very small AAA disfavored stacking sites. So we can basically put triangles that are connecting these dark blue spots there, and you can see exactly this lattice appearing. So there's some sort of super moire modulation. And I should have said that these peaks are so narrow that it's a sign that there is really lattice relaxation into a single uniform moire periodicity, that there aren't two peaks, there's no reason for these two angles to be correlated, so that you only see one single narrow peak is a sign that actually you've locally relaxed into a particular moire periodicity within these domains. Okay. So I'm running out of time, so let me just quickly mention a couple other key points, and then I'll wrap up. Interestingly enough, so theoretically we can predict in the absence of strain what is the size that one expects for these super moire domains. And if you just take in as input parameter this local twist angle and ask what do you expect and what's the experimental size of these domains relative to the theoretical size, actually we see domains which are much larger, or which are larger than theoretically predicted. So what could be causing this? Well, if there's some twist angle mismatch between theta 1,2 and theta 2,3, actually that only tends to decrease the size of the super moire domains. So that doesn't explain anything in our data. But actually, these samples, as I've said, are very, very susceptible to strain. So this is just a plot of a uniform biaxial strain. And you can see that the super moire domain size, what we expect is this dashed line. But depending on the specifics of the strain that's applied to one of these layers, you can get divergences in the size of these domains. Now, we can't say, so you can reproduce this experimental data with many, many different strain configurations, many, many different magnitudes, but overall the phase space of possible strains that could give rise to enlarged domains is actually fairly small. Now, okay, so the takeaway message is that strain is actually growing the size of these uniform domains. Now, we got a little bit lucky or unlucky. I don't know what to say. The tip crashed, unfortunately. But so we had to thermal cycle this thing. There were some other dings to the sample, but we put it back into the microscope and we measured it again in this area denoted by this black box here. So very similar area, same size scale for all of these images. And we took the data again. And you can see that right there, now all of a sudden, the domains are more uniform and they're much, much larger. So actually, the size of these super Moiré domains grew from about 400 nanometers to something closer to 600 or 650 nanometers between these dark blue spots. And so I think this is kind of interesting. We don't know exactly what happened, how reproducible this is, but clearly the system is very, very susceptible to strain, and you may even possibly just by thermal cycling be able to grow the domains to get to this, what you asked about earlier, can you get one single domain to see the quantum anomalous Hall physics in transport? So anyway, this is kind of cool, and certainly this super Moiré modulation says something about the transport behavior, namely you expect that along these domain walls, you have topological boundary modes that depend on the specific Valley and sublattice indices. And I think for timing reasons, I'll only mention the punchline, which is we can measure simultaneously AC measurements of electronic compressibility. That's what I've been showing you so far. Or we can measure on DC timescales. And as long as the sample resistance is low, as long as it charges well, then these two measurements should agree with one another. But if the sample is too resistive and you modulate on some AC timescale, the gate voltage charge may or may not be able to come in to screen the electric field that you're applying. So this can enhance the apparent inverse compressibility and gap size, and indeed we see that in our sample. And interestingly enough, if you take a line cut through this super Moiré modulation, the amount of enhancement varies as a function of the local stacking configuration. So the enhancement is largest in the domains where we expect truly a gapped behavior, and it's relatively small along the domain walls where we expect possibly topological boundary modes. We can't say whether they're topological, but at least the domain walls are clearly more conducting based on this comparison of AC and DC. So I'll end there and just acknowledge all of the people who were involved in these measurements, particularly a couple of graduate students, Jesse Hoke and Yifan Li, and postdoc Yuan Hu, who came actually from Ali's lab here at Princeton. We had many, many helpful theoretical discussions on this magic angle bilayer graphene twist decoupled from monolayer graphene with Taylor Hughes, Barry Bradlin, and Julian Mayman, who has since moved on to Stanford University, where we've had really helpful conversations with Trizep, Tom, Zoe, and Charles. So with that, let me just end with my conclusions that I think this twisted trilayer graphene system is really quite flexible and can be, I think, quite interesting. You can go anywhere from twist decoupled layers to learn something about the low twist angle limit, about the generic behavior as a function of twist angle of these correlated bands. And possibly this is a sort of this helical trilayer graphene platform might be a good way to engineer networks of topological boundary modes in the future, and has also been proposed as an interesting system for fractional churn insulators because the bands themselves are very flat and topological. So thank you for your attention. Yeah.
For a nice talk. So, as a function of magnetic field, these phase boundaries of like the insulating phases, like the correlated insulating phase or the penetrating ones, how do they develop? Because in a way, like magnetic field and Moiré potential should cooperate, right? Because they both flatten the band, or the.
Yes. So are you asking with a particular sample in mind? This sample or that one? I have magnetic field data that I can pull up. That's why I'm asking.
For the twisted or this monolayer, but I mean, I guess both phases.
Yeah. So I guess okay. I can go back to that slide where I had some. There we go. This guy. So I think you're asking, do the bands become relatively flatter here in a magnetic field? Is that right? Yeah, so I don't think it's well known. So this is very much deep in the Hofstadter regime. So electronic interactions matter a lot. And the energy scale for electronic interactions in these graphene systems is pretty large compared to the bandwidth and even compared to the separation to the remote bands. So there have been attempts to calculate including interactions, for example, from Oscar Vafek recently, to try and figure out what do you expect for magic angle bilayer graphene in various different regimes and various different strain configurations. But the calculation itself is extremely involved and quite difficult, and you get different changes in shapes of the Hofstadter spectrum itself as you fill it with carriers. And so I guess I don't have a crisp experimental statement. We see churn-ins later, so it seems to be relatively flat, like magic angle bilayer graphene, but whether it's, what exactly is going on in this limit, I don't have a crisp answer for.
Thanks.
So in that two pair of bands that you have C equal to 1, churn number 1, can you induce a gap using like a HPN or something there?
The pair of bands with churn
Yes, we had this band that's retro.
case.
Yes.
So so it's sort of like the TMD systems, I would say, that we heard about before. Actually, kind of even magic angle graphene in certain limits has non-zero churn bands. So this already these uniform domains already break C2Z symmetry. So this is what the HBN is doing, or the aligned HBN is doing in magic angle bilayer graphene. So in fact, all you really need to do is have interactions be strong enough to polarize you into a particular value, and then you should get exactly that splitting. Yeah.
To get the isolated flat band instead of just pair of.
With interactions, you should be able to. Yeah.
Maybe I misremember but when we were showing what's it called, like the trilayers where you could figure out the magic angle, which was different to the electron on the holder,
Yes.
right? Maybe my eye is deceiving me, but are there features further up, like further up in the distance? Right there, yeah. Like that looks the beginning of some sort of fake features. Is that something that you have thought about? And they seem to be modulated in exactly the same way.
That is a great question. I do see something squinting also at my screen. Yeah, I think you're talking about this up here. Is that right? I do see something, and that is not. I would have to ask the graduate students how much they looked into that. If they looked in any detail, I am not aware of that. And you're right, it's interesting because this is quite far from what you would otherwise have called the magic angle criterion. So just to bring the twist angle map, this is closer to 1.35 or 1.4 even up there. Now, I'll caveat it that we don't know what the other twist angle is in that location. So it's possible still that we're somewhere along this funny phase boundary. If the other twist angle is relatively smaller, then that would tend to, if I must have this somewhere close by, hopefully, this guy. So as you decrease one twist angle, here the magic angle is going to be 1.1, just like in magic angle bilayer graphene. Here it grows to be something larger. So it's possible that the other interlayer twist was a little bit lower in that region, and maybe there is really magical physics. But as far as I'm aware, we did not look super carefully there. Yeah.
Is the degree to which the angle you don't know the twist angle of, obviously within sort of that 2 to 5 degree region, does that matter, or do you have a way of determining that other than maybe putting direct contact between?
Right. So going the wrong direction. Yeah. So you can see here the twist angle variation for the one that we can characterize is about 0.5 degrees. And I'd say that's kind of typical over micron length scales for a typical device. These things are hard to make uniform. The helical trilayer graphene was a miracle device. So I would naively expect that the variation should be on that order of magnitude for the other angle. Now we can do certain things. So for example, I don't know, is it in this one? Not super visible in this one. So sometimes you can see moire of moire features. So there, sometimes you can get doubling of incompressible states. Actually, I'm not 100. No, I think this is its own churn insulator. So I don't see it in this. Well, no, you see a little dip there. So there's something. So you can try and back out. And we don't have a crisp answer for this. But based on the moire of moire features, you can figure out what is that associated moire wavelength. That tells you something. If you know one of the twist angles, it gives you some pattern of what the other twist angle could be. And we have a lot of spatial dependence that we're still sifting through. This is all, I'm presenting you new stuff, so apologies for not having a good answer to this. So we don't have a crisp number, and for any given location, I would say, again, unless you get lucky that the moire of moire features are there and also allow you to pinpoint specifically what that other interlayer twist is, it's going to be hard to back out because the twist angle is large enough, it's well beyond the accessible gate voltage range that we have. We may be able to say a little bit, but probably not a lot about that. And it probably does matter, which was your original question.
Other questions? No? So let's thank Professor Feldman again.